Okay guys, so this is going to be chapter 16, Oxidation and Reduction Reactions. All right, so definitions of oxidation. So one definition of oxidation, though it's not the one that's used scientifically that much, is simply the gaining of oxygen. So that's where the word comes from. And so we all know oxidation is rusting. Also, oxidation is anything that's burning. A carbon-based compound undergoing combustion is an oxidation reaction. But the actual definition of oxidation is the loss of electrons. And so when something loses electrons, it loses negatives. If we subtract a negative, it becomes positive. And so what we're looking for is we're looking for the substance to become positive or more positive, or for the oxidation number, which we'll look at in a minute, increases. So when something is oxidized, it actually loses electrons. And so if we look here at magnesium, magnesium does not have a charge here. It has a charge of 0. And then over here it's 2+. And so that would represent something being oxidized. All right, and then the opposite of oxidation is reduction. And reduction is the gain of electrons. And so when something gains negatives, it becomes more negative. So we're looking for the oxidation number, again, we'll go over that in a minute, to go down. So here we have copper being +2, and then over here we have copper being 0. There's no charge shown. So that means that it went down and it was reduced. So reduce literally means to go down. And so that's what you're looking for. You're looking for the oxidation number to go down. So oxidation and reduction summary. Notice that oxidation and reduction has to occur together. So if one substance loses electrons, then that other substance has to gain them. So whatever is losing the electrons is basically giving its electrons to whatever is being reduced. So we have something being oxidized, this thing shoots out electrons, and it's going to whatever is being reduced. So they actually feed into one another. So with the reaction that we've been looking at, magnesium gets oxidized while copper is being reduced. So magnesium is giving its electrons to copper. So a couple of terms. Oxidation agent is an agent that makes the other substance become oxidized. And so what I used to always say is a travel agent books your flights and gets you tickets for shows that you're going to go to and stuff like that, but they don't actually travel with you. They just assist you in the traveling part. So the oxidizing agent is whatever is being reduced, because as it's being reduced, it's allowing the other substance to be oxidized. And the same thing goes for reducing agent. The reducing agent is the substance that gets oxidized, and so it makes the other substance become reduced. So here in this example, we have the reducing agent. So this is what gets oxidized because hydrogen is gaining oxygen. So we see that it gets oxidized. And then this is the oxidizing agent because it's allowing hydrogen to get oxidized. So because it's giving itself to hydrogen. And so this is a little bit different than the way we'll really be looking at it, because we're not always going to have oxygen in an oxidation reduction reaction. So let's look at a couple of these examples. This stuff at the bottom basically says what I was explaining in bigger, more sciencey words. Helpful ways of memorizing this stuff. Oil rig means oil, or oxidation is loss, reduction is gain, and both of those of electrons, so that's oil rig. Leo the lion says grr. Another one, lose electrons oxidation, gain electrons is reduction. I can never remember those, so they don't ever really work for me. I mean, I know them now after 20 years in chemistry, but when I first learned stuff, I can't learn it that way. All I ever remembered is that reduce means to go down, so that must mean it gains electrons. And then I knew that oxidation was the opposite of that. So that's the only thing that I ever remembered. And so here's a summary of what we're going to be looking at. So oxidation states is a way to identify oxidation and reduction reactions. We also call them redox reactions. So that's short for oxidation reduction. All shared electrons are assigned to the most electronegative element. And then a number called the oxidation state or the oxidation number is computed for each element, and don't confuse oxidation state with ionic charge. So a substance doesn't have to be ionic for us to assign oxidation states to it. We can assign oxidation states to CO2, and that's not an ionic compound, but we can assign it to them. Okay, and so the easiest way to assign oxidation states is to follow the rules. So here are the rules. You might want to write these down somewhere, and they are hierarchical, which means that if any two rules conflict, we always follow the rule that is higher in. So rule 1 beats rule 2. All right, so the oxidation state of an atom in a free element is 0. So this magnesium is 0. That's the oxidation number for that. And the oxidation state of an ion is equal to its charge. So here, because phosphorus is showing a charge, that means that it has a -3 oxidation number. Now this is a molecule, and it doesn't show a charge, and so it has to be 0 for that. Because if it did have a charge, both oxygens in that molecule would have the same charge, and that oxygen, so if it was to be -2, it would have to say that it was -4 up here, which it doesn't. So because it says 0, there's no charge shown. That means that the oxidation number of that oxygen is 0. And number 2 says the sum of the oxidation states must equal the charge. If it's a molecule, the sum of the oxidation states must be 0. So when we look at phosphite here, I know that the sum of the oxidation state of whatever phosphorus is and whatever these oxygens are has to equal +3. So when we add them all together, it has to give us +3. Whereas in carbon dioxide, it has to equal 0 when we add them all together. That's all that means. So whatever the charge you see, the sum of all of them have to be the charge. And that's why in this O2, each of those had to be 0, because that's the only number we can add together to end up getting 0. And since it's all the same atom, they have to have the same oxidation state. Whereas in this one, the phosphorus can be a different oxidation number than the oxygen. So that doesn't necessarily mean they're going to be 0 here. Fluorine will always be assigned -1. It's the most electronegative element, and so it's going to be -1. So in this, fluorine would be -1. That means that sodium has to be +1 because they have to add up to 0, okay? And then here, this fluorine has to be 0. That violates this rule, but rule 1 trumps it, okay? So since there's no charge on this fluorine at all, each of these fluorines have to be 0. So that when we add them together, we get 0. Oxygen will be -2 unless it's in a peroxide. So oxygen here is -2, and if we have 3 of them, then that means together that would be -6. So when we add all of this together, we want to get 0 because there's 0 charge on this molecule. So this sulfur right here is going to be +6. So sulfur would be +6, and then oxygen would be -2, and those would be the oxidation numbers for those atoms there. So the reason why we looked at the -6 is that we could balance out the charge and get a total charge of 0 because of rule number 2 on this slide. All right, now this is a peroxide. So peroxide is when oxygen looks like this. All right, so this oxygen is going to be -1, and we have 2 of them that would be -2. So this hydrogen would have to be +1 each to give us +2. So that means that oxygen would have an oxidation number of -1 in this molecule, and hydrogen would be +1. All right, it says hydrogen will be +1 unless it's with a metal. If it's with a metal, it's -1 because then it's the most electronegative. And elements in ionic compounds will have an oxidation state equal to their charges. So hydrogen is with a metal here. Magnesium is a metal, so it's going to be -1. And we've got 2 of them, so that would be -2 altogether. And then magnesium is going to be +2. Here, oxygen is -2. So each one of these hydrogens would be +1. So notice when I give the oxidation numbers of the individual elements, I'm giving it of what each element would be, not what the sum of it is. All right, so here's some examples. So for this magnesium, it's given as +2. For this phosphorus, there's no charge, so they're all 0. So then for this oxygen, each oxygen is -2. And so altogether, that would be -8. And we want 2 negatives left over after we add them together because the sum of the oxidation numbers has to equal a charge. So that means that this sulfur is going to be +6. So sulfur here is +6, and each oxygen is -2. All right, K2S, this is an ionic compound, and sulfur has a -2 charge as an ion, and potassium is +1. And to double check, we have 2 potassium, so that'd be +2, and then -2, and so it equals 0, which is the charge on the compound. And so potassium is going to be +1, and sulfur is -2. All right, here on chromium +4, it's just going to be +4, and that's it. All right, chromate, we have -2. With all together, it'd be -8, and we want -2 left over. And so this chromium would have to be +6. All right, oxygen here is -2, and we have 7 of them, so that'd be -14. But we want 2 negatives left over. So it means this chromium altogether has to be +12 because 12 and 14 is -2. But we have 2 of them, so that means each chromium is +6. So chromium will be +6 and oxygen will be -2. All right, S2O4, 2 negative, so that's going to be -8 altogether because each oxygen is -2. And we want 2 negatives left over. So that means that this altogether has to be +6. So that means each sulfur is +3. So sulfur would be +3, oxygen would be -2. And so if we add these two together, we get -2. That's how I knew that this was going to be +6. Whatever number it would take to get -2 left over for the charge would be what the positive number is going to be. All right, oxygen here would be -2. So that's going to be -6 altogether. We want 1 left over. So this chlorine is going to be +5. So chlorine is +5 and oxygen is -2. Oxygen here, -2. So that's going to be -20. And then phosphorus would have to be +20. And so each phosphorus, if we have 4 of them, and all together we want +20, that means each phosphorus is +5. And then aluminum nitrate. So this is usually where students get confused because you don't remember your charges the way you should. So this is aluminum 3+ and nitrate 1-. So right here for aluminum, I know that it's 3+ already. And I know that nitrate is -1 because I memorized them. So oxygen would be -2, and this would be -6. So this nitrogen has to be +5 to give us that -1 charge, right? If this is all +5 here, +5 and -6 is -1. Now I can do this all together, but it gets very confusing. And so I prefer to take this apart, especially when I have 3 of or 2 of one of those polyatomic ions. So here aluminum is +3, nitrogen +5, oxygen -2. So determining what gets oxidized and what gets reduced in a reaction. So in terms of oxidation states, we define oxidation and reduction as follows. An increase in oxidation states means that it was oxidized. So if lost electrons, if it loses electrons, it loses negatives because electrons are negatives, then it gets bigger, the number gets bigger. If it decreases in oxidation state, so if we add negatives, then that means the number goes down. So here we're adding electrons, and here we're subtracting electrons. So reduction means a decrease in oxidation state, oxidation means an increase in oxidation state. So if we look at this again with new eyes and I assign the oxidation state of +2, 0 to that magnesium because it doesn't have a charge, 0 to that copper because it doesn't have a charge, and +2 to this magnesium, then I can see that magnesium went from 0 to +2, so it was oxidized, and copper went from +2 to 0, and so it went down, so it was reduced. All right, so determine what is oxidized and what is reduced, and determine the oxidizing agent and the reducing agent. So if we look at this, calcium here would be 0, oxygen would be -2, hydrogen would be +1, because this would be -2, and then each hydrogen would have to be +1 to cancel out those charges. Hydrogen here at the end, I'm going to skip down here to the very end, would have to be 0. And then the calcium hydroxide is an ionic compound because it's a metal and nonmetal. So we have calcium ions and hydroxide ions. And so calcium would be +2. And then hydroxide, oxygen is -2, and hydrogen is +1 to get that negative charge left over. All right, so calcium went from 0 to +2. And so calcium is oxidized. And if it's oxidized, that means it's the reducing agent. Okay, and then hydrogen went from +1 to 0. And so it was reduced. And so it's the oxidizing agent. All right, and then we have sodium and fluorine. So sodium here is 0, fluorine here is 0. This sodium is +1. This fluorine is -1. So sodium went from 0 to +1, so it was oxidized. And then fluorine went from 0 to -1, so it was reduced. And if it gets oxidized, sodium would be the reducing agent. And if it's reduced, fluorine would be the oxidizing agent. All right, so a couple more examples. Hydrogen here is 0, oxygen here is 0, and then oxygen in water would be -2 because it's always -2 unless it's a peroxide, and then hydrogen would be +1 each. So hydrogen went from 0 to +1, so that means that it's oxidized. And then oxygen went from 0 to -2, so that means it's reduced. So hydrogen would be the reducing agent and oxygen would be the oxidizing agent. All right, so zinc would be 0 here, chlorine -1, hydrogen +1. Notice that I'm ignoring these coefficients. They don't matter. Chlorine is -1, zinc would be +2 because we have 2 chlorines, each at -1. This is ionic, so you can just use charges. And then hydrogen is 0. So zinc went from 0 to +2, so that's oxidized, so it's the reducing agent. And then hydrogen went from +1 to 0, so it went down, it was reduced, so it is the oxidizing agent. So this is actually a picture of zinc in HCl right here.